Hello and welcome yet again. My name is Evuka and today we'll continue from where I stopped last time. In my last video, I said I was going to talk about Retrieval Augmented Generation, RAG, and as it relates to the SecAI Plus exam. So we've been hearing a lot about RAG. So in this video, we'll talk about RAG, what RAG is, and its importance when it comes to cybersecurity, and also how or some of the questions that can come up in the SecAI Plus exam. So let's get started. So why RAG in the first place? RAG is a framework that allows an LLM to reference external up-to-date information during response generation. So it's not the picture that we see there. It's a framework that allows for access, number one, to fresh information, right? We have access to fresh information with a RAG system. And also, we can factually ground and prevent hallucination. Because if you ask a normal LLM without factual information or enough references, like a particular question, it doesn't know what to do. It might hallucinate. It might give a wrong answer. But when you give it fresh and factual information, feed it into the database of the LLM, right, or the training data of the LLM, then we can have a factually grounded information. The next is relevance, accuracy, and quality. This is the main problem that RAG actually solves. Number one, hallucination. Number two, up-to-date or updated information, and relevance, accuracy, and quality of generated data or generated responses. Okay, so instead of training a large language model from scratch when you have new information, RAG provides real-world enterprise data. That means you can feed in your own data into the RAG pipeline, and then it can generate for you relevant, accurate, and quality information based on the prompt context window, which I'll explain right now. So look at this. Look at this situation, right? When we have like a RAG pipeline, right? The first thing we do is that we have our external information. We have our external data. For example, a legal firm, right, have will have their own legal data or up-to-date legal information, fed into chunks. We'll break that data into chunks and feed it into the embedding model. So when we do this, right, we now have an embedding model that does a cosine similarity check to check and match, whatever information that you fed in with the database, right, before you retrieve. Essentially, with RAG, what we are doing is that we don't want to ground any response without an external or factual source, right? So we are using this mechanism to ensure that the large language model, which is this model here, stays factually correct and accurate, right? But without a RAG pipeline, we just see that the user can query the large language model, and based on the old training data, it might hallucinate or give a wrong response. So this is not what we want. This is not what we want at all. But we want external knowledge fed into chunks into the LLM, so that in step one, when the user makes a query, it references this external source in step two, and then checks the vector database in step three and retrieves the document back to the user. This is the core essence of RAG, right? So, what are the types of RAG, right? We have the agentic retrieval, just like a messenger, the agentic messenger and the classical messenger. So, within the agentic framework, the RAG pipeline is assisted with query planning, multi-source access, and structured responses. That means the LLM it's LLM assisted. This is the focus here. LLM assisted query planning. But in the classic RAG system, it uses hybrid search or semantic ranking or the cosine similarity check I mentioned for retrieval, right? So these are the two types or the current two types of retrieval within the retrieval augmented generation pipeline or retrieval augmented generation RAG. Okay. So I also want to talk about the fact that RAG can be poisoned. Look at this study here, poisoned RAG. Poison rag was a recent study that showed that you can actually poison a rag, that external database that I mentioned. So this external database here can be poisoned by an attacker, right? An attacker can poison this external knowledge source or database and force the model to produce or review wrong or poison data, right? So there are specific threat factors, right, that affect RAG systems or that affect RAG pipelines. The first one is embedding-based prompt injection. In the course of this class, I'll also explain the full concept of a prompt injection attack. But it's just like you are crafting malicious inputs, right, to manipulate the vector search and retrieval process. So that means the retrieval process has been compromised with an embedding based prompt injection attack. Just like, oh, I know the new information that's going to be fed into the model, and then I poison it, and then it forces an embedding based prompt injection. Another one is model inversion attack. This way, an attacker can attempt to reverse engineer the system by querying the model to reconstruct sensitive original source documents from their numerical embeddings. So remember the embedding model. We can reverse engineer the the system or the RAG system to review personal information or original source documents. And this is one of the threat factors that affect RAG pipelines. And these kind of questions might also come up in the exam. So you may feel free to look at this paper, and it's very interesting to show you and to see that even the RAG pipelines can be vulnerable to injection attacks or poison or backdoor attacks. So how do we prevent this RAG or all this unauthorized system? So we have the external database here. We have the external database here, and then we have the model, right? So how do we secure and ensure that any user that queries the model, right, does not suffer poison here, right? Or does not suffer like a malicious response, or does not get a malicious response. First one is role based or permission aware RAG, right? So you only retrieve based on authorized persons. So only authorized persons can retrieve. That's one way to prevent and ensure that the model only retrieves and displays information that the specific querying user has authorized permission to use. The second way is RAGAS, Retrieval Augmented Generation Assessment. It's like a validation framework used alongside GEval to test guardrails before and after deployment. So when in the course of this channel as well, I will explain more on evals and what GEvals mean. But essentially what we are doing here is to validate before we deploy the model, right? Before we deploy the model, we want to be sure that the model does not review personal information. So that's a preventive or a technical control that says, oh, before everybody outside starts getting infected or starts seeing the vulnerability of our RAG pipeline, we want to test, we want to validate first before deployment. So this is similar to this method here is similar to what we have during in the generic or normal security governance, right, where you assess or where you assign role-based access to RAG pipelines, because if an unauthorized user gets access to the RAG pipeline, he or she can poison the model and then causes a very big vulnerability. So I've explained the RAG, right? Essentially what RAG is doing here is to get fresh, new, validated, factual data as the knowledge source, right? Break it into chunks and feed it into the model. The embedding model is the model that generates whatever responses it generates, right? And then the model checks the vector database to cross-check, to have a cosine similarity check and be sure that the reference document matches what the user has requested, and then retrieve the the response to the user. For example, if I ask, what is the largest city? What's the largest city in Mali, for example, right? Google or the original training data, this one here might not have this information, right? But with a good and factual external source, we can have those broken chunks that the model can pick from and retrieve correct factual, data, that is fed into the model. Okay. So I'll just go to the next topic. The next topic I wanted to also cover is natural language processing, right? So here we talk about large language models. We talk about small language models. We talk about generative adversarial networks, and then we talk about GANs. Okay. So the first thing about NLP is that it's the branch of AI that gives computers the ability to understand text and spoken words in much the same way as human beings can. Natural language, right? So the same way human beings understand natural language, is the way that these computers have the ability to understand what's going on or to understand text and spoken words or generated words. So the NLP is powered by the transformer architecture. The exam does not expect you to know and understand all of the ongoings of the transformer architecture, but the key thing there is that unlike models that read text word by word, transformers use self-attention to analyze entire sentences at once, understanding the deep context and intent behind the words. Usually, you have to read every word one by one. But with self-attention, right, this paper is a very groundbreaking paper in the world of AI, right? We find out that we can actually read sentences and contextualize sentences at once and then generate or understand what is going on or give these computers the ability to understand what is going on as it goes or as it sees those words and text. So LLMs are built upon this same natural language processing, right? NLLs predict words from left to right. For example, the cat likes to sleep in the right. So we have a multi-class or a numerous number or a million or a trillion number of next word prediction ability or tasks, right? But with large language models, right, we can frame the next word prediction as a multi-class or machine learning problem, right? Yes, it's a classification task. So the cat likes to sleep in the is the input, right? And then we have a neural network that is tasked with the responsibility of predicting the probability of the next word. So this is what an LLM essentially does, predicting the next word. For example, the quick brown fox. The next word is jump. We all know it's going to be jump, right? Because the large language model has the ability to assign a probability of that word jump to the next word. So look at the ability here. The ability of the word ability here is 0.002. The probability of the word here is 0.071. The ability of the word box is the highest probability, 0.085. And then just like that. So since box has the highest probability, the large language model then predicts box as the next word. So this ability of the LLM helps with so many various tasks in cybersecurity as well, such as defense, offense, right? When you come to defense, you can actually generate codes, right, that defend the network or defend your infrastructure. For offensive cybersecurity, LLMs are very helpful for crafting, red team situations or even, strength testing what you have built or both your network or your software or your application. So this is the fundamental idea of large language models. So these large language models, right? We all know some of them. Some of them are owned by OpenAI. The GPT family. So we have the GPT-1, GPT-2, GPT-3, GPT-4, and we can see the diverse applications that is giving birth to, right? For Meta, right, we have the Llama 1, 2, 3, right? Right now we have Llama 3, right? And we see some of the applications, that are available within the Llama 1 to 3 model. For Google, we have the MedPalm and all of those models as well that are birthed out of the Google large language models. Then we also can categorize these large language models, according to open weight LLMs, right? And closed weight. So open weight models can be found on Hugging Face. You see the ones for finance, you see the ones for literature, you see the ones for mathematics, you see the ones for different domain, for healthcare, you see the ones for cybersecurity as well. I remember in my last video I pointed out some two cybersecurity, LLMs, right? And you see that you can, for open weight models that are characterized with high control, you can easily get one and build for yourself, or even deploy privately on your home network, or school network, or whatever network that you're running, right? And the cost might be marginal because you don't have to pay for the GPUs and TPUs and whatever you might be using to process or run those large language models. And you have more privacy. You are not sending your queries to a company that you don't know, right? But with the open weight models, right, you have controlled privacy and speed, right? You can also maximize your own speed with open weight models because you don't have to route through many hubs or networks to get a response. But with cloud hosted APIs, the cost is something. People run into a lot of cloud, running costs these days, and you see that the privacy is also pay as you go, and the speed is moderate and also fast, So this is one good thing with cloud hosted APIs. Sorry, I know I said that the local ones might have good speed, because I've experienced good speed with local models as well that I've used for my research and work. But cloud hosted APIs can also provide reasonable speed. So please pardon me on that. For the small language models, right, they are the opposite of the large language models. So these large language models are characterized with very high parameter numbers. So parameters, right? It can be 70 billion parameters, 40 billion parameters, 30 billion parameters, right? The size of the model is extremely huge, right? But with small language models, we experience cost efficient, customizable, edge deployable language models and solutions, right? And their architecture is compact, is really small, or not too small, but small, right? And we have an experienced low computational cost and adaptability, right? So this is one good thing about the the small language models, right? For a small language model, you can see something like 7 downwards billion parameter models. A good thing and very important thing I also want to note here is that LLMs, these large language models, can guide the deployment of small language models. They helped in guidance collaboration. So a small language model might not understand or get full context on its own, right? So a large language model, right, can help or provide guidance to a small language model. And the same also happens with a small language model, right, which can provide context to a large language model, because a large language model might not know the domain specific nature of things that are maybe in the edge network or in edge scenarios. For example, a farmer, right? The large language model in most big models, or maybe Google Gemini or whatever, might not understand the sensor measurement in maybe a smart farm. So the small language model deployed in the small smart farm, right, can collaborate or provide expert knowledge, to the big large language model. So let's think about the small language model as a student, right, and the teacher. Sometimes the teacher might not know everything, and then the student might say, okay, hey teacher, this is what it is. And also the teacher is tasked with the responsibility of providing guidance to the student. So this is the scenario, or the guidance collaboration that we experience when we use both small language models and large language models together. So let's look very shortly for examples of these small language models. If you look at this literature, right, small language models can still pack a bunch. It's like a recent study. If you go to page 25 is where I want us to look at very quickly. And then you see some examples of these models, and you know uh, uh, what their size and the data sets that they were fine tuned on, right? So you see Llama 2, right? It's 7 billion in size. This is as a baseline, and the equivalent size is 7 billion, right? Tiny Llama, right? 1.1 billion. Mistral 7. So we see a range of Zephyr 7, Phi 1, Phi 1.5, Phi 2, occur like that. You see that we don't even exceed a very high range of billion parameter models, right? The highest one here is Mistral, right? The highest one here is Mistral, right? And we can see Mistral has a 47 billion parameter weight or size. And you see that these models, small language models, still exceed or still perform very good when it comes to high reasoning tasks like reasoning, maths, knowledge, understanding, safety, truthfulness, and so many other things. So this paper is actually very interesting, providing us with context, right, and the usage and how these small language models are very useful, right? So if you want to deploy something lightweight, something that needs to work on an edge device. I mean, even these small language models even can work within Raspberry Pi or very low edge devices. So this is why they are very useful to provide cost efficiency, number one, customizability, edge deployment, since they are obviously compact in nature, low computational cost, and very adaptable. The next one we want to talk about is generative adversarial networks, right? It was written by Ian Goodfellow many years ago, like I think it's 2017, right? The idea is that I'm going to read the part of the abstract for you to understand or give us a full idea of GAN. So we propose a new framework for estimating generative models via an adversarial process in which we simultaneously train two models, a generative model G that captures the data distribution, and a discriminative model D that estimates the probability that a sample came from the training data rather than G, right? So we have the generative model G, right? The generative model G captures the data distribution, and a discriminative model D that estimates the probability that the sample came from the training data. This is the core and fundamental idea of generative adversarial networks. It must have a generator and a discriminator. So these two adversarial components, right, helps to complete the generative adversarial network in its fullness, right? So where is this scan actually meaningful or useful? Number one, we use it to create new data, right? And go beyond classification to generate content, because we have classification algorithms, right? And we also need something that helps us to generate new data, right? It's useful in art, gaming, healthcare, and data science, right? Even cybersecurity as well. It helps you to generate new cybersecurity samples, right? Based on the data that you give it. So let's imagine that we give a very random input, right, into the generator, right? The generator generates fake images that are not true. And then meanwhile, you have your own real images on one side, and then it compares the discrimination, checking the probability variance, right, and helps us to know whether it's a discriminative or a real photo, right? This way, we are able to generate new information and also useful for adversarial resilience or defense, right? So this is the basic idea of what the exam might ask you about generative adversarial networks. But if you want to learn more about these concepts, I have attached some papers in this in this slide to help us to, you can read up further and you understand the core mathematical idea and framework and technologies, even the results discussions of these core ideas. So today I have covered I've talked about RAG, right? I've talked about the vectors, the attacks that affect RAG pipelines. Talked about the technical controls for them. We also talked about large language models. We talked about small language models, and then we just finished generative adversarial networks. So now I would like us to have some scenario-based questions. Okay, so this is question one. Please pause the video and give it a try. Question 1. During the data processing phase of a new machine learning intrusion detection system, the security team implements rigorous data verification. What is the primary security fix they are attempting to mitigate by ensuring the training dataset has not been covertly altered? So from this answer, so the answer here is B, data poisoning. Answer is B, data poisoning. So the security implements this, and what is the primary risk they are trying to by ensuring the training data set has not been altered? So it's data poisoning. Because if the data has been poisoned, right, and then it has been altered and the training data has been corrupted, right? So we just look for the keyword here and know the answer that it is data poisoning. It can be model inversion, it's not a prompt injection attack, it's not excessive agency. The answer is simply data poisoning. Question 2. Feel free as well to pause the video and give it a try. Question 2 says, as generative models become capable of creating hyper-realistic deepfakes, organizations are using digital watermarking as a proactive strategy for content authentication. To be effective, a watermark must survive common edits such as file compression, audio trimming, and resizing. Which core principle of watermarking does this describe? Traceability, invisibility, robustness, and provenance. The answer is robustness. Robustness. So robustness ensures that your watermark must be working, like it must be functional, right? It must also guarantee functionality to what is being watermarked. For example, I have a music file or I have whatever it is, it should not stop the functionality of the original file that is watermarked. So that's why it is robustness, not other options. Okay. Question 3. Please feel free as well to pause and give it a try. A financial institution wants their internal large language model to answer the CFO's questions regarding the latest proprietary financial audit playbooks. They need to achieve this without the immense computational cost of retraining the entire foundation model. Which architectural framework provides this capability while mitigating hallucinations? I know you already know the answer. This should be very, very simple. Right. Okay. So freshness, remember, the freshness talked about the latest, information. This information could be PDFs, markdown files, image, whatever it is, but they are added as external database, to provide more context for the model, and provide and avoid hallucination. So whenever you see hallucinations and latest or new information, just know it is RAG. Okay. Question 4. An enterprise has successfully deployed a RAG architecture using a vector database to store embeddings of their private corporate data. However, a threat actor begins querying the model iteratively in an attempt to reconstruct the sensitive original source documents directly from the numerical embeddings. What type of attack is this? A. Embedding-based prompt injection. B. Model inversion attack. C. Dynamic poisoned RAG. D. Data poisoning. This one is a little bit tough, but the answer is B, model inversion, right? So poison RAG is there's no, the most correct question right here is model inversion attack. Why? Because the actor queries the model to reconstruct the sensitive original information. So that reconstruction intention makes the answer to be model inversion attack. Question 5. To harden a new RAG system, security architects integrate identity and access management into the vector retrieval loop. This implementation utilizes document level security to ensure the large language model only retrieves and displays context documents that the querying user explicitly has clearance to view. Which defense control does this describe? A. RAGA's assessment. B. Permission aware RAG. C. Token limitation. D. Prompt. Yes. So the answer here is very simple, which is permission aware RAG. Okay, because it's the security architect integrates identity access management. You know, retrieves and displays context of the queries explicitly has clearance to view. So it's based on permission, and the answer should be permission aware RAG. Question 6. The security team needs to deploy a large language model into endpoints. That's edge deployment, maybe a drone, to assist in local triage. The model must have a compact architecture, preserve high data privacy, and be highly customized to internal network logs rather than the general internet knowledge. Which linguistic architecture is best suited for these tasks? Large language model, small language model, GAN, or transformer? You already know the answer. I don't need to say this answer. You already know. It's SLM. Okay, B. Okay. The last but not the least, when generating synthetic data to train a new SOC anomaly detection system, an architecture is used that simultaneously trains two distinct models. One model attempts to create fake data that mimics the real training distribution, while the other model attempts to estimate the probability that a sample came from the real data rather than the fake source. What is the architecture called? We should all know this answer. I don't even say it twice. Answer is C, GAN, Generative Adversarial Network, that uses a generator and a discriminator. Alright, so these two, is the core component of a generative adversarial network. Okay, so thank you for watching this video. We are almost at the end of the exam objectives for part 1. So we have covered this one, we have covered this as well, we have covered this, we've covered this one. We will be entering 1.2, right? We're still in 1, but our next video will look at the importance of data security in relation to AI. And oh no, sorry, I think we've covered this as well. We've covered the data processing, the structured and so, and then we'll talk about this one as well. Yeah, we've done 1.1 and 1.2. So our next video should look at 1.3. So guys, get ready with me, and I'm excited to share the little that I know in this domain. And please feel free to like and share this video, or also like subscribe to encourage the work that we do here together. And if you know anyone also preparing for this exam, please feel free to share my video with them. And my Telegram group has the PDFs and my study guide that I use to pass my own exams. So thank you very much for watching. Bye.